Imagine standing right there on the edge of a vast, churning river. The current's just formidable, unyielding. And you're looking across to this burgeoning city that's just crying out for connection.
Right.
And then imagine dreaming of a link. Not just any link, but something so audacious, so monumental, that it would define nature itself, push human ingenuity right to its absolute limit, and ultimately cost a family almost everything. Today, we're not just talking about steel and stone. We're digging into the incredible human will, the sacrifice, the groundbreaking engineering behind one of the world's truly iconic structures, the Brooklyn Bridge.
It's such a story.
Welcome to the Deep Dive. Today, we're embarking on this, extraordinary journey into the epic human and engineering story of this magnificent structure.
Yeah.
Our mission is to really pull out the most important nuggets of knowledge, the key insights from the sources you provided. We want to help you understand the monumental challenges, the sheer perseverance required, and the groundbreaking innovations that really defined these kinds of projects back in the 19th century.
Absolutely.
We know David McCullough's Pulitzer Prize-winning book, The Great Bridge, is sort of our conceptual guide here, a fantastic resource for this topic.
It really is the touchstone.
And we'll be enriching that perspective with other detailed accounts, looking at the engineering, the human elements of this whole saga. We're going to dive deep into how this 14-year project, which was just fraught with peril and personal tragedy, pushed the very boundaries of what humanity thought possible, and how it became this defining symbol of American ambition, industrial might.
What's fascinating here, I think, is that the Brooklyn Bridge isn't just a feat of construction, right?
Yeah.
It's a profound narrative. It's woven right into the fabric of a city's identity.
Yeah.
So this deep dive, it's going to reveal the audacious ingenuity, the immense risks, and that unwavering resolve that turned what, let's be honest, many considered an impossible dream into this enduring reality.
Totally impossible at the time.
It really offers these timeless lessons, doesn't it? About long-term project management, the courage you need to innovate, and just the incredible human capacity to overcome unimaginable adversity. It's more than just a crossing. It became this testament to what's possible when a society, sets its sights on an ambitious goal and just commits to seeing it through despite all the odds.
Okay, let's unpack this then. Let's maybe start by setting the scene a bit. The 19th century itself.
Right, the context.
Exactly. This was a truly transformative period, wasn't it? A time of just relentless innovation, the world industrializing at this incredible pace.
Wow, explosion, yeah.
And with all that rapid change came this intense and widespread admiration for engineering feats. It wasn't just about function. There was a genuine awe, right, for these new massive creations that seemed to conquer nature.
Yeah, people were mesmerized. You're right. They were captivated by the power and the scale of what human ingenuity could suddenly achieve.
It wasn't just bridges and railways either, was it?
No, exactly. And the sources really highlight this. In this period, the admiration wasn't limited to grand public works or ornate bridges. There was this broader cultural appreciation for large-scale, functional, technically impressive structures, even things that might seem, mundane to us today.
Like what?
Well, for example, in Europe, things like anonymous industrial building, especially factories, coal bunkers, and grain elevators, also roused admiration. That tells us something important.
What does it tell us?
It tells us that the public and even the architectural community were just captivated by the sheer scale, the intricate mechanics, the technical prowess required for these structures, regardless of their sort of artistic intent.
Right.
This cultural shift, this pervasive sense of wonder at human-made marvels, it really laid the crucial groundwork for the public acceptance and, ultimately, the celebration of monumental projects like the Brooklyn Bridge. It fostered an environment where such grand ambitions could actually find support.
Okay, so the public was primed, in a way. And at the very heart of these colossal undertakings, whether it was a factory or this unprecedented suspension bridge, were these visionary engineers and architects.
Right, the key figures.
These individuals weren't just following blueprints. Often they were inventing the blueprints as they went, pushing materials, pushing mathematics, right to their absolute limits.
Totally.
And one name that truly stands out in this era, particularly with grand American bridges, and definitely our story today, is John Roebling.
The visionary.
His vision for spanning the East River, which, as you said, many considered sheer madness, was foundational. He really embodied this era's spirit of bold, innovative engineering.
And if we connect this to the bigger picture, it becomes clear it wasn't just about individual genius, right? It
Yeah.
was also about a rapidly developing philosophy of design that was profoundly impacting how engineers conceived and executed these projects.
How so?
Well, thinkers like Viollet-le-Duc, for instance, they contributed significantly to an architectural philosophy that prioritized what he called structural rationalism.
Structural rationalism. Okay, what does that mean in practice?
It meant focusing intently on the logical, inherent strength and efficiency of a structure. It was about letting the structural requirements, the way forces would move through a building, letting that dictate its form.
Ah, okay.
So the building itself becomes this logical, truthful expression of the forces it was designed to withstand. This move away from purely decorative or classical forms was absolutely vital for engineers like Roebling,
Why vital?
because they were pushing the very boundaries of what was physically possible. For them, understanding these forces wasn't just academic, it was literally the difference between an enduring monument and, well, catastrophic failure.
Right. So it wasn't just about aesthetics, about making something look pretty or fit some classical ideal.
No, not at all.
It was about ensuring the very form of the building, its silhouette, its mass was dictated by its fundamental function and the immense forces it needed to handle. It was rigorous, almost scientific.
Exactly. The beauty emerged from the perfect, elegant resolution of these complex structural challenges. The structure was the statement.
That's a good way to put it.
And this raises an important question then. What was the image, the social standing of the engineer during this era?
Yeah, how are they seen?
Well, far from being seen as mere technicians or, skilled laborers, their role was profoundly respected. In a way, it was almost philosophical.
Philosophical. Yeah.
As described in one source, the engineer spends much of his time intimately involved with those eternal principles which we call the laws of nature.
Wow.
It speaks to this profound blend of scientific rigor, a deep understanding of physics and mechanics, and an almost, spiritual dedication to understanding and harnessing the fundamental laws of the universe.
So they weren't just builders.
No, they were interpreters of nature's rules, wielding that knowledge to reshape the world.
That's a powerful image, grappling with the laws of nature. It really challenges any notion of engineers as, dullards, which some later critics might have suggested. Instead, folks like John Roebling were seen as individuals who, through sheer intellect and audacity, could bend those fundamental laws to create something entirely new, practical, and often just awe-inspiring. Something that had never existed before.
Precisely.
But surely, even with that respect, there must have been immense public skepticism for a project of this scale and cost. With so many unknowns.
Oh, absolutely. Huge skepticism.
So how did these engineers, beyond their technical genius, manage to gain and maintain that public and political backing for something so audacious? Especially when critics might have just seen it as an impossible pipe dream, a waste of money.
That's an excellent point. While they were respected, the scale of a project like the Brooklyn Bridge meant public opinion was a constant battleground. Roebling, beyond his engineering brilliance, possessed this incredible ability to articulate his vision.
Ah, the salesmanship.
Yes. To explain the seemingly impossible in a way that resonated with politicians, financiers, the general public, he was a master of persuasion, painting this vivid picture of the economic prosperity and the civic pride a bridge across the East River would bring.
So he was campaigning for it.
Constantly. He published pamphlets, he engaged with civic leaders, he confidently presented his calculations. He essentially became an evangelist for his own vision. He understood that to build something unprecedented, you needed more than just brilliant engineering.
You needed buy-in.
You needed unwavering belief and the ability to inspire that belief in others. He was selling a future, not just a bridge.
Okay, so the vision is set, the context is there. Let's get to the actual building. When it came to a project like this, connecting two cities across a waterway like the East River.
A notoriously difficult waterway.
Exactly. The single most challenging part wasn't necessarily the towers and cables we see, right? It was what lay hidden beneath those swirling currents.
The foundations. Always the foundations in water.
Building across that kind of water meant conquering the riverbed itself. The foundations were arguably the most challenging, the most dangerous, and the most technologically pioneering part of the whole thing. Demanded totally new solutions.
Indeed. And the fundamental principles of dealing with water foundations are incredibly ancient, but they highlight the enduring nature of the problem, regardless of the era.
How so?
Well, Andrea Palladio, the great Renaissance architect, he laid it out in the Four Books of Architecture centuries ago. He said, basically, if buildings are to be in rivers, the sand and gravel will be altogether useless because the water, by its continual current and flood, is always shifting their bed.
Makes sense.
We must therefore dig until a firm and solid bottom be found. Bedrock, ideally.
And if you can't find it easily,
Well, his historical solution involved piles made of oak, driven in until their ends reach the solid ground upon which one may build.
like giant stakes into the riverbed.
Exactly. This historical perspective just underscores how deep and stable these foundations needed to be. A challenge that, while ancient in principle, would demand revolutionary technology to achieve for the East River's unprecedented scale and depth.
That's a fascinating link, ancient wisdom right up to the 19th century. Because while the principle of finding solid ground was ancient, the challenge of building across a turbulent, busy waterway like the East River
Yeah, with its deep, muddy, shifting bottom and constant ship traffic.
demanded something far beyond traditional methods. So what exactly were these cutting-edge yet incredibly risky innovations that let them conquer the riverbed in ways no one had ever dared before?
Okay, this is where it gets really intense because to deal with these underwater challenges on this unprecedented scale, 19th century engineers developed ingenious, though often frankly terrifying new technologies.
Terrifying how.
These innovations, while brilliant, came with significant human cost and risk. They pushed the limits of what was understood about human physiology. The primary innovation for foundation work beneath the river was the caisson.
The caisson. Okay, explain that.
Right. For those unfamiliar, a caisson is essentially this massive, watertight chamber, open at the bottom, which is sunk down into the riverbed.
Like a giant box.
A giant bottomless box, yeah. Then compressed air is pumped into this chamber, forcing the water out and creating a dry, albeit perilous, space for workers to actually dig out the riverbed and build the foundation upwards.
So it's like working in a bubble underwater.
Think of it as an enormous inverted diving bell. It allowed construction to happen far below the surface, right on the river bottom.
Wow.
And a prime example illustrating the principles of this innovative yet hazardous deep water construction comes from Isambard Kingdom Brunel's work on the Saltash Bridge in England. A bit earlier, but same principles.
Pharrell again. He pops up everywhere.
He really does. He designed this great cylinder, 35 feet in diameter at the base, for the central pier's underwater portion. And it wasn't just simple, it was a sophisticated tube within a tube, using experience from earlier projects like the Thames Tunnel.
Okay, break that down. Tube within a tube.
So the inner tube of this cylinder functioned basically as a diving bell where the masons worked. It was kept clear of water by pumps and ventilated by a pipe that went all the way up. This gave them a relatively stable, though still very confined, environment.
Got it. And the outer tube.
The critical innovation was the space between the inner and outer tubes. This annular space, 4 feet wide, was sealed and pressurized using a pneumatic apparatus.
Compressed air again.
Exactly.
Yeah.
Powerful air pumps pushed compressed air into that space, keeping the water out and allowing workers to operate in a dry environment beneath the river.
Okay, so why the two tubes? What was the advantage?
Well, this setup offered a significant advantage for worker safety and efficiency, at least in theory. It meant that only the workmen clearing the mud in the annulus as the cylinder descended had to work under air pressure.
Ah, so the masons inside were spared the pressure.
Largely, yes, spared that inconvenience, as the source puts it. Plus, it avoided the necessity of passing all the material for the pier through airlock doors, which really streamlined the construction process.
Still sounds incredibly dangerous.
Well, unbelievably hazardous. Despite this advanced tech, the sources paint this vivid picture. The debris which fell through into the workings from the bed of the river, pieces of bone and china, an old shoe buckle, and finally the sheaf of a block and a shovel left no doubt as to the state of the ground above.
Good grief. Things just falling in.
Constantly. This constant threat and the dependence on the structure itself meant the entire operation, quote, depended on the shield, which alone prevented immediate collapse. It was truly work at the edge of human endurance, battling unseen forces, the chaotic randomness of the riverbed itself.
That incredible detail from Brunel's work really illustrates the kind of deep water, pressurized environment that Brooklyn bridge workers must have experienced, but maybe even worse, on a grander, more perilous scale in its caisson.
Exactly. Imagine being down there, sometimes over 70 feet below the surface of the East River, facing unimaginable pressures, the constant threat of collapse or fire, and the insidious, then unknown physical tolls that this compressed air work would take on the body.
And the Brooklyn Bridge caissons were huge, right?
The largest ever built up to that time. Immense timber structures, literally the size of city blocks. John Roebling designed them, but it was his son, Washington, who descended into them day after day, leading the crews and ultimately enduring the horrific consequences.
So these weren't just bigger, they were deeper too.
That's right. The caissons for the Brooklyn Bridge were revolutionary not just in size, but in the depths they reached. About 44 feet for the Brooklyn Pier, which was already deep, but an unprecedented 78 feet for the New York Pier.
78 feet down, the pressure must have been enormous.
Unbelievable pressure. And this is where the unseen perils became tragically manifest. While the exact mechanisms weren't fully understood at the time, workers began to suffer from this mysterious and excruciating ailment they called caisson disease.
Or the bends, right?
Exactly, the bends. The symptoms were horrific: blinding headaches, excruciating joint pain, paralysis, seizures, even death.
What was actually causing it?
It was caused by nitrogen bubbles forming in the bloodstream and tissues when workers ascended too quickly from the compressed air environment back to normal atmospheric pressure, like opening a soda bottle too fast, but inside your body.
Oh my God.
And the sources, while they don't detail caisson disease specifically for the bridge, they give us historical context for the general dangers of industrial work back then. De Re Metallica, an old mining text, describes dangers of cobaltum being extremely corrosive so that it consumes the hands and feet of the workmen unless they are well protected.
So they knew work could be dangerous, but this was new.
This was something entirely new and terrifying. Doctors on the site, frankly, were ignorant. They often administered alcohol or opium, which probably made things worse. Dozens of men died. Many, many more were permanently crippled.
And Washington Roebling himself.
Tragically, yes. Washington Roebling, who spent countless hours down in the caissons supervising the work, became a prime victim. He developed a severe, debilitating case of caisson disease that left him largely paralyzed and unable to even visit the bridge site for the rest of its construction.
Unbelievable. That's the profound human cost embedded in these grand engineering triumphs, isn't it?
Absolutely. A stark testament to the risks taken in the name of progress.
Okay, so they somehow managed to get these foundations built despite the horrific cost. Building the Great Bridge wasn't just about figuring out how to sink foundations deep into a treacherous riverbed. It also required meticulous selection and testing of the right materials for this entirely new scale of structure.
Absolutely critical choices, yeah.
These choices had to withstand forces and last for a century in a way that no earlier bridge had ever faced.
And what's fascinating here is that the 19th century was very much a period of intense material experimentation in bridge building. Engineers were learning, often through, well, trial and error and sometimes bitter experience, what worked best under different conditions.
Like iron.
For instance, yeah, a great many cast iron arch bridges were built during this time, and for smaller spans, they were quite successful. But engineers also quickly recognized the limits of these materials.
How so?
Brunel, him again, he consciously avoided cast iron for his Maidenhead railway bridge. He was afraid that the vibrations of the trains would crack the brittle cast iron. Made sense.
So what did he use instead?
He opted for brick arches, which apparently worked very well. This example perfectly illustrates that pragmatic, experience-driven approach to engineering. Real-world performance and understanding material properties dictated the design choices, trying to anticipate and mitigate potential failures before they happened.
That's a fascinating pragmatic approach, isn't it? Prioritizing real-world performance over maybe newer, flashier ideas. But given the immense pressure to innovate back then and the allure of cutting-edge materials, how difficult was it for engineers like Brunel, or especially the Roeblings, to resist the latest trends?
Good question.
Or maybe to stick with proven, older technologies, or to champion radically new ones that were still largely unproven? Was there a strong push from investors or the public to always use the newest and best, even if it was untested? That must have created tension.
That tension was absolutely constant. For Brunel, his established reputation probably gave him some latitude, but for John Roebling and the Brooklyn Bridge, the stakes were arguably even higher.
Because of the scale.
Exactly. Roebling faced immense pressure to justify his choices, especially his revolutionary decision to use steel wire for the main cables.
Steel wire. That was the big one, wasn't it?
That was perhaps the single most critical material innovation for the bridge. At the time, wrought iron was the standard for big structures like this, but Roebling's calculations, based on his experience with earlier suspension bridges he'd built, like Niagara and Cincinnati.
Right, he had form.
He did. His calculations convinced him that only steel possessed the tensile strength and the elasticity required for that monumental, almost 1,600-foot main span over the East River.
But steel was new back then.
Relatively new, yeah. Expensive and largely untested for this kind of purpose, on this scale. He had to convince a skeptical board, he had to demonstrate through extensive testing, and he literally had to create the process for spinning these high-strength steel wires into massive cables on a scale never before attempted.
So he was inventing the manufacturing process, too.
Pretty much. It was a true leap of faith, but it was backed by meticulous science and a profound understanding of material properties.
So beyond the physical materials, the theoretical understanding of structural forces was paramount. And Roebling's design was a masterclass in applying these principles, right?
Absolutely. It was well understood, for example, that an arch is or should be entirely in compression,
Pushing force outward.
whereas the underside of a beam is in tension, pulling force. When Roebling envisioned spanning the East River, he wasn't just thinking bigger. He was fundamentally redefining how materials could manage these immense forces within a sort of hybrid structure.
Hybrid how?
Well, consider the suspension principle itself. Unlike a traditional arch, which works by pushing forces outwards, Roebling's design brilliantly distributed tensile forces, that immense pulling stress through those monumental steel cables.
Okay.
Imagine millions of pounds of weight from the deck, the traffic, all trying to rip those cables apart. The challenge was ensuring the steel could withstand that continuous pulling without fracturing.
And that's where the steel wire came in.
That was the game changer. Far stronger, far more elastic than the wrought iron used in other bridges back then. It allowed for unprecedented spans and load capacities.
And the towers.
The bridge's majestic granite towers, on the other hand, they functioned as colossal compression structures, pushing vertically down into the bedrock through those massive caisson foundations, anchoring the whole system, transferring the immense weight safely to the earth.
The tension in the cables, compression in the towers.
Exactly. But Roebling's innovation didn't stop there. He also incorporated diagonal stay cables, radiating from the towers down to the deck.
The ones that make that sort of fan pattern.
Precisely. And they weren't just decorative, they provided crucial rigidity against dynamic loads like wind, heavy traffic. They helped mitigate shear forces and sway.
Shear forces being.
Sort of slicing or sliding forces. These stays were a critical addition, often overlooked, but vital to the bridge's stability and longevity. It essentially made it a hybrid between a pure suspension bridge and a cable-stayed bridge. Way ahead of its time.
So this means that the bridge's majestic appearance, it's almost cathedral-like granite towers and that elegant sweep of cables.
Beautiful, isn't it?
It really is. It was all underpinned by an incredibly sophisticated dance of forces, meticulously calculated to ensure its immense strength and longevity. Every beam, every cable, every massive stone was placed with a precise understanding of its role.
Poetry and engineering, as you said, the structure's form expressed its function with just unparalleled grace and strength. And if we connect this to the bigger picture, the methods of construction themselves were evolving alongside the materials and the structural understanding. And this created a tension between traditional craftsmanship and the demands of industrialization.
How did that play out?
Well, historically, craftsmanship was incredibly high. Viollet-le-Duc noted in his lectures on architecture that each stone was finished, molded, and sculptured before being laid. This fostered a workforce of skillful and intelligent masons.
Pride in the work.
Immense pride and a deep understanding of every component and how it fit into the whole. Quality was paramount.
But industrial projects needed speed, scale.
Exactly. And with new, faster methods and the intense economic pressures of huge projects like the Brooklyn Bridge, there was this constant risk of losing those valuable traditions and the knowledge they nurtured. Sometimes, as one source puts it, the necessity of making the jointing accord with the various members of the architecture was no longer imperiously felt.
Meaning creamers were cut.
It could lead to ignorance among workmen and a total want of harmony between the jointing and the architectural feature. The relentless push for speed and scale could, ironically, undermine the very quality the project sought to achieve. It threatened to turn skilled craft into mere assembly line work.
That's a familiar tension even today.
Absolutely. It highlights this crucial lesson for any large project, past or present, that whenever the immediate necessity of observing a principle ceases to exist, the principle, however valuable, is lost.
So how did the Roeblings handle that on the bridge?
Well, for the Brooklyn Bridge, this tension was acute. While the sheer scale demanded industrial processes, the Roeblings, both John and Washington, were apparently unyielding in their demand for meticulous quality. Washington, even from his sickbed, obsessively oversaw every detail he could.
From his sick bed.
How? And this is where we absolutely have to acknowledge the extraordinary role of Emily Warren Roebling, his wife.
Ah, yes, you mentioned her stepping in.
She effectively became the de facto chief engineer. She would relay Washington's instructions, but she also learned the engineering herself. She would inspect the quality of the steel wire, for instance, ensuring each strand met Roebling's rigorous specifications. She fought battles over bad materials provided by contractors.
Oh.
It just demonstrates that maintaining high standards of quality and attention to detail against the pressures of scale and speed is a constant, vigilance-demanding battle. It's a timeless struggle between efficiency and excellence that every monumental undertaking has to navigate.
What an incredible story. Okay, so this brings us squarely to the human element. Projects of this scale, like the Brooklyn Bridge construction.
More than just engineering marvels.
Absolutely. They were immense exercises in human will, extraordinary feats of management, and monumental challenges requiring just unparalleled personal and professional resilience. 14 years. The complexity must have tested everyone involved, often right to their breaking point.
You're right. And what's fascinating here is that tension between grand ideals and commerce. It's a recurring theme in engineering. Figures like Brunel, apparently, spent his life trying to mix them and succeeded better than most men.
Ideals in commerce, the vision versus the budget.
Exactly. It speaks to the constant negotiation engineers faced, balancing the soaring ambition of their vision with the stark practical realities of budgets, demanding stakeholders, political infighting, the sheer logistical complexities of construction.
And that was true for the Brooklyn Bridge.
However present. John Roebling's initial vision was breathtaking, right? But turning it into reality required navigating constant political battles, financial panics, securing funding from both New York and Brooklyn cities, each with its own competing interests. Achieving that balance between these often conflicting forces was, and remains, a hallmark of successful long-term project management.
And beyond the high-level negotiations, the politics, there were the very real day-to-day challenges of labor, right? Team dynamics.
Absolutely. Securing a reliable and skilled workforce for such specialized, dangerous, unprecedented work was a huge hurdle in the 19th century, especially given the sheer scale of the operation.
Any examples of that?
Well, we see this challenge clearly in Brunel's earlier experience building a portable hospital somewhere. He was unable to find any local labor which he could trust.
Really?
With the consequence that the hospital was built entirely by the little gang of 18 men who had been sent out from England.
Just 18 guys built a whole hospital.
Apparently. It's not just an anecdote. It demonstrates the absolute necessity of specialized, dedicated, highly trusted teams for complex, pioneering work, especially when the scale or conditions are unusual.
And for the Brooklyn Bridge, it wasn't 18 guys.
No way! The labor force swelled to thousands. A diverse mix, skilled stonemasons, steel workers, and of course the often immigrant, tragically exploited caisson workers. Managing such a vast and often transient workforce in incredibly hazardous conditions was a monumental task in itself.
What kind of hazards, besides the bends?
Oh, fires erupted in the caissons, accidents from falls, falling debris were common, equipment failures were a constant threat. All of it claimed lives and limbs throughout the 14-year project.
It just sounds brutal. It speaks to the immense dedication required, often by a select few, to keep things going, ensure quality, especially when local resources might be lacking or the risks were just so profound.
It wasn't just about hiring bodies. It was about cultivating and maintaining a capable, committed, and frankly courageous team under extraordinary circumstances.
And this is where the human drama of the Roebling family itself really takes center stage, isn't it?
Absolutely. You simply cannot tell the story of the Brooklyn Bridge without chronicling the profound sacrifices of the Roebling family.
Starting with John Roebling.
John A. Roebling, the visionary, tragically died right at the beginning of the project. A ferry crushed his foot while he was surveying the site.
Just a freak accident.
A freak accident, and despite the intense pain, apparently he refused most conventional medical treatment, relied on his own water cure therapies, contracted tetanus, which eventually claimed his life.
Oh, no.
So the torch and this immense burden then passed to his son, Washington A. Roebling.
Who's also an engineer.
A brilliant engineer in his own right, yeah. He'd studied caisson technology in Europe, he knew the risks, and he threw himself into the work, supervising those dangerous operations down in the compressed air chambers beneath the East River.
And his dedication was unwavering.
Unwavering, but as we discussed, the toll was devastating. He became gravely ill with caisson disease. It left him paralyzed, confined to his home in Brooklyn Heights, largely unable to speak or move without great difficulty, watching the bridge rise through binoculars from his window.
Just devastating.
But this is where the story takes an utterly remarkable turn, truly highlighting human perseverance. Washington's wife, Emily Warren Roebling, stepped into this completely unprecedented role.
We touched on this, but her role was just incredible.
Yeah, beyond incredible. With her husband incapacitated, Emily didn't just nurse him back to a semblance of health. At his instruction, she began to study higher mathematics, the intricacies of cable construction, stress analysis, the full scope of the bridge's engineering.
She learned it all.
She learned it all. She became Washington's eyes and ears on the site, his voice to the foremen and contractors, his brilliant mind translating his often silent instructions from his sickbed.
So she was running the project.
For years, Emily effectively managed the entire construction project, dealing with political factions, mollifying skeptical engineers, ensuring the meticulous quality her husband demanded, fighting off attempts to remove him as chief engineer. She was, in essence, the de facto chief engineer.
A role virtually unheard of for a woman in the 19th century.
Completely. It's a testament to her incredible intellect, her resilience, her unwavering dedication to her husband and his vision. It's one of the great, often undertold stories of engineering history.
It really is astonishing. And it's a powerful reminder that even with groundbreaking innovation and, fierce competition among engineers.
Like Brunel and Stevenson.
Right, exactly. You mentioned that earlier. The sources say the two greatest engineers of the day, Brunel and Robert Stephenson, were in constant opposition in public, yet neither ever allowed this to influence their long and unbroken friendship.
Yeah, Brunel wrote about the delightful experience of meeting Stevenson on a perfectly friendly footing and discuss engineering points amidst their incessant personal-professional contests.
That's amazing. It tells us that the human element, collaboration, mutual respect, even that healthy rivalry is essential, isn't it, to pushing the boundaries of what's possible.
Definitely. These individuals, despite personal challenges and public contests, shared this deep understanding and respect for each other's work and for the monumental task at hand.
Okay, so if we connect all this to the bigger picture, the story of building the Brooklyn Bridge inherently teaches us so much about long-term project management, about overcoming just unimaginable adversity.
These aren't just historical footnotes, they are absolutely timeless lessons.
How do they connect to, say, modern ideas about project management?
Well, modern project management, like what's outlined in the Project Management Body of Knowledge, the PMBOK guide, which is kind of a global standard,
Okay.
it emphasizes the focus on value. Recognizing value as the ultimate success indicator and driver of projects. And value isn't always just money, right?
Right.
It can be a financial contribution, sure, but also a measure of public good or the customer's perceived benefit. The Brooklyn Bridge certainly delivered massively on all those fronts.
Immense economic value, huge public good connecting the cities.
And an unmatched perceived benefit for the citizens of New York, Brooklyn, and really the nation. This principle, defining and driving toward value, it's truly universal. Applies then, applies now.
And what else?
The PMBO guide also stresses the continuous need to plan for how to address uncertainty and risks. Projects, especially huge ones over long durations like the Brooklyn Bridge, they're not static. They never go exactly according to plan.
No kidding.
Plans need to be revised or new plans developed to account for events or conditions that emerge. The 14-year construction of the Brooklyn Bridge was just a masterclass in this adaptability.
How so? Give me examples.
Well, think about it. From the unexpected geological challenges they found in the riverbed, to the devastating impact of caisson disease, to the sudden death of John Roebling, the incapacitation of Washington, the political infighting, financial panics, scandals over materials,
Just one thing after another.
an unending barrage of unforeseen challenges, the ability to pivot, to learn from setbacks, to integrate new information, new technologies sometimes, and just maintain the project's momentum despite these monumental adversities. That was as vital then as it is for any complex project today.
It's a testament to incredible resilience.
And an unwavering commitment to the ultimate goal. That's project management under fire.
Wow. Okay, so let's try and bring this deep dive together. Our exploration into the context of building a great bridge, like the Brooklyn Bridge, has revealed this incredibly rich, complex tapestry. Human ambition, engineering brilliance, relentless perseverance.
It's all in there.
From conquering treacherous riverbeds with these innovative, dangerous pneumatic marvels, to selecting and testing materials like revolutionary steel against the forces of nature, to the profound human drama of the Roebling family's sacrifices.
John, Washington, Emily.
To managing colossal teams, navigating fierce professional rivalries. These projects were just a profound testament to human will. The stories, whether it's Brunel's cylinders or the harrowing challenges of the East River crossing, they highlight this period of incredible ingenuity and the immense, often tragic, sacrifices made to achieve the impossible.
And if we connect this to the bigger picture, structures like this, they don't just solve a transportation problem, do they? They become embedded in the collective consciousness.
Yeah, they become symbols.
Enduring symbols of what a society can achieve when it dares to dream big and commits to that long, arduous path of creation. The East River bridges, and especially the Brooklyn Bridge, they aren't merely crossings. They become defining features of a city, shaping its identity, reflecting its aspirations for generations.
That's powerful.
They remind us that engineering isn't just about building things, it's about creating legacies that inspire, connect, and fundamentally alter the human experience.
So considering that immense human and technical effort, the sacrifices, the innovations involved in building a project like the Great Bridge, a project that literally spanned generations of a family's dedication. What modern challenges do we face today that require a similar blend? That same audacious vision, relentless perseverance, groundbreaking engineering.
That's the question, isn't it?
What structures, maybe physical, maybe metaphorical, are we building now that will, a century from now, represent the soul and ambition of our time?